Reinforcement learning is an approach to machine learning in which a system learns from data rather than from explicit programming. In reinforcement learning, an agent interacts with its environment and, based on observations about its own behavior, can alter its actions in response to the rewards given. This way, such successful decisions will result in the process being reinforced because it solves the problem the best. There are several subcategories within the topic of reinforcement learning, with two of them being single and multi-agent reinforcement learning. Single-agent reinforcement learning, like the name suggests, is when a single agent interacts with an unknown, randomly determined environment. Multi-agent reinforcement learning, on the other hand, is when multiple agents collectively learn, collaborate, and interact with each other in an environment. There are several reasons why one should use reinforcement learning and several reasons why one should not use it. You should use reinforcement learning when you are trying to find which situation needs an action, when you want to discover which action yields the highest reward over the longer period, and when you want to figure out the best method for obtaining large rewards. You should not use reinforcement learning when you have enough data to solve the problem with a supervised learning method, and when a real-world problem has no good simulation available. It's important to keep in mind that reinforcement learning is computing heavy and time consuming, so it should not be used when you want solutions immediately.
The math behind reinforcement learning. Neural networks. Neural networks consist of layers of neurons represented by matrices, with matrix multiplication representing traversing through the neural network. The value function is then defined by the last layer's distance from the objective, with the objective being discretely known for any given input. You then optimize by backpropagation, or gradient descent, which refers to usage of gradient vectors, which you take the neuron relative to the value function, the last layer's distance from the objective, to minimize the distance from the objective. And then by repeating this over and over again, you descend through the plane towards the local minimum being an optimal point. With reinforcement learning, it's a lot harder to reach the optimal point because the optimal point is determined by a series of states connected by actions, with different states having different rewards, and you wanting to maximize your rewards. So the value of any given state isn't just the current state, but it's also your future states. To account for this, we take our current state and we look at our future states, our probability of reaching them based on our policy and our actions that you can take. And then you also account for you also reduce their reward for futures based on how far they are into the future. And then each of these future rewards, you then have its own value function. So you go forward a good bit, but from there you can have a value function that accounts for future rewards. And you can use that to then maximize your policy and achieve an optimal policy.
So all this looks good on paper, but how do we actually make it work? Well, to begin, we can use some already existing libraries such as OpenAI Gym to take care of the environment stuff and PyTorch or TensorFlow to handle the neural networks. And we can actually check that this example does work for a single agent situation. See, this seems simple enough, right? Well, looking at the code just begs the question, can we make this even simpler? And luckily for us, the answer is yes. We looked at backend libraries just now, specifically PyTorch, but we're more interested in libraries that do everything that we've done on the last slide for us. And there are some of them that actually do this for multiple agents as well. Specifically, RLlib is a particular outlier. So as mentioned before, RLlib is a library that does multi-agent reinforcement learning for you. It also integrates really well with other libraries that handle multi-agent reinforcement learning environments, such as Petting Zoo and Unity. You can see some of them here. And on the right side, you can see a minimally working example of RLlib, and note that this takes just about 3 lines of code only.
Introducing multiple agents into the RL problem creates a number of issues that require specialized algorithms to solve. One such problem is called non-stationarity. Most reinforcement learning algorithms assume the environment can be modeled as a Markov decision process, which assumes the environment is only affected by the agent's action and the environment's transition probabilities. However, the other agents can affect the state in the multi-agent setup. This slows model convergence and invalidates some techniques. It also introduces the problem of communication between agents. As more communicating agents are added, the curse of dimensionality may set in. The curse of dimensionality refers to failures that occur in machine learning only when working with high dimensionality data. Furthermore, agents in a real-life multi-agent system cannot always communicate with unlimited bandwidth. Independent Q-learning, fully observable critic, and learn to communicate are 3 classes of algorithms for multi-agent environments. Independent Q-learning treats each agent independently and considers the others part of the environment. While simple to implement, it does nothing to address non-stationarity. Fully observable critic methods employ one value function. that considers the states and actions of all agents. It resolves the non-stationarity problem, but is vulnerable to the coercive dimensionality. Approaches where the agents learn to communicate via gradient descent are better at avoiding the coercive dimensionality, but may impair learning or fall into a local optimum of not communicating.
As you can see, there are many different ways that reinforcement learning can be applied to everyday life. Some I'll talk about will be the Cloud AutoML, which is essentially like it helps businesses with limited expertise or funding for like advanced uses of ML and AI. Basically, it helps simplify the step for reinforcement learning for companies to more efficiently run things. As you can see below, it takes a data set and it brings it to the AutoML, and then it generates a prediction based on what is put into the AutoML. And as for the OpenAI Gym, basically it's a toolkit for developing and comparing reinforcement learning algorithms. So essentially, like it helps developers develop their reinforcement learning skills better by using and performing computations such as adding multi-digit numbers and reversing sequences. And as you can see in the image below, basically the agent performs an action which goes into the environment, and then it creates like it develops like whatever rewards that it should receive. And for autonomous driving, this uses reinforcement learning to create an intelligent vehicle that's able to look at the state that it's in, such as traffic, whether a pedestrian or anything is around the vehicle, and then it takes that information and uses reinforcement learning to create an action based on what state it's in, and it'll basically come out with the rewards, which is a safe, efficient, and comfortable driving experience.